Hello and welcome to another lab of CE 3105 Mechanics of Fluids Laboratory here at Texas Tech University. In today's lab we'll be looking at fluid flow measurements through pipes, and my name is Venturimeter and I'm your instructor for this class. So flow rate is one of the most basic measurements that we do with fluids, especially when fluids are flowing. And the most simple way to measure flow rates is simply to collect a known volume of the fluid or liquid over a given time. So this works great for liquids, particularly because when they flow, we can capture them in a container and then measure how much volume we captured and what time it took for it to flow into that container. And if we divide that volume by time, we get our flow rate. While it's typically easy to do that, a lot of times we are interested in measuring flows in line through pipes. So as long as there is a discharge where we can measure these flows, we can use the gravimetric measurements or the volumetric measurement. But oftentimes when we are interested in the middle of a pipe, we cannot simply undo the pipe and then make a flow measurements and then put it back again. That's not going to happen. So we need to make inline flow measurements. Gravimetric or the volumetric measurements work fine when the volume is small. When the volume is large, clearly it becomes a little bit unmanageable to capture all the water over a given period of time. So intuitively, while the volumetric measurements of measuring volume per given time is easy, there are some practical difficulties in practical civil engineering problems. So we need to find ways to measure flows in line in a pipe. Just as a refresher, the typical units of flow rates can be CFS, cubic feet per second, liters per minute, gallons per day. So anything, it's volume over time. So that's your basic flow rate measurement. So to measure flow, we often make use of several indirect methods. Methods that make use of conservation of mass, which is the continuity equation, as well as the conservation of energy, which is the Bernoulli's equation. Remember from your fluids class that the flow rate is the fluid flux times the cross-sectional area. For a pipe that's flowing full, the fluid flux is same as the velocity, so Q is equal to area of cross-section times V, and that area is measured normal to the direction of flow or perpendicular to the direction of flow. The conservation of energy is basically stated using the Bernoulli's equation, and what the Bernoulli's equation basically says is that your pressure head, the velocity head, and the potential head, so the total energy contained in a fluid at any given point in a pipe is P over gamma, which is your pressure head, plus V squared over 2G, which is your velocity head, and then plus Z, which is your potential head. So this corresponds to the pressure energy, this corresponds to the kinetic energy, and Z corresponds to the potential energy. And as a refresher, hydraulic head is equal to energy over unit weight. So the total head at any given point in time, in a pipe is a constant, and that's what is the basic Bernoulli's equation. So we'll make use of Bernoulli's equation, which is a conservation of energy, as well as the continuity equation, which is a conservation of mass, to look at ways in which we can do these flow measurements in line. So the first device that we are going to be looking at is what's known as a Venturimeter. And a Venturimeter typically is a modification within your pipe where you have a convergent section and then a divergent section. So you're making the flow to converge down to a smaller cross-sectional area, and then you're going to let it diverge it back and get back to its original diameter or original velocity. So from conservation of mass or the continuity equation, we know that if the flow rate is constant through this system, then this has a larger cross-sectional area, so the velocity here is going to be smaller compared to this section, section 2, where the velocity is much faster because of smaller cross-sectional area. And if this pipe is lying parallel to the ground, then my Z1 is equal to Z2, so they cancel out. And clearly, since the velocity is small here, the pressure must be larger here compared to here. Most of the energy is in the form of kinetic energy, so your pressure energy is going to be smaller. Okay, so using continuity equation, as well as understanding that this pipe is parallel to the ground surface, so there is no potential energy lost or gain in the process, using Bernoulli's equation and continuity equation, we come up with an equation for our flow rate, which is a function of your cross-sectional areas A1 and A2, as well as the change in pressure between those two cross-sectional areas, A1 and A2, and then gamma is the specific weight of water and g is the acceleration due to gravity. So again, this form of Bernoulli's equation assumes that there is no head loss, so energy is conserved as it moves through the Venturimeter, which is an assumption. And using that assumption and using the continuity and Bernoulli's equation, we can calculate the flow rate. The wide-angle diffuser, which is the second part of it, where you start off from a lower cross-sectional area and slowly diffuse out to a larger cross-sectional area, essentially works in the same way, just in reverse. Clearly the pressure here is much smaller and the velocity is high, and if I go to some point in the wide angle diffuser, once it's been diffused out to a larger pipe, then the cross-sectional area is large, which makes the velocity small, and then there is a subsequent increase in pressure. So by measuring pressure heads, or the P over gamma terms, before and after the water enters and exits the Venturimeter, and knowing the cross-sectional areas, we can calculate our flow rate. So this is one indirect way of measuring flow rates. So Venturimeter and wide-angle diffusers are two essentially very similar instruments, or like in a very similar apparatus that we can put inside the pipe or modify the pipe and make flow calculations really quick from the knowledge of Bernoulli's equation and continuity equation. The orifice plate is another way to measure flow, and orifice plate takes up a much smaller footprint, so it is very small, so it works well in places where you cannot really contract and expand the flow back in a pipe. So if your pipe section is small and you don't have enough of a length to expand and contract your pipe and then expand it back, you make use of an orifice plate. And essentially an orifice plate is a plate with an opening, and clearly the cross-sectional area in the plate is much smaller compared to the cross-sectional area in the pipe, and as the water flows through the opening of the orifice pipe, there is some head loss because some of the flow lines that are hitting this plate have to essentially curve and make their way into that smaller cross-sectional area. So as they do that, they're encountering some friction, and they're going to encounter some loss because their energy is being absorbed by the plate. When the water hits the plate, some of that energy gets absorbed. So if we write our Bernoulli's equation again before and after, I have P1 over gamma plus V1 squared over 2G plus Z1, P2 over gamma plus V2 squared over 2G plus Z2 plus a head loss term. And that head loss we are assuming is proportional to the change in the velocity. And we can again rearrange our Bernoulli's equation, and also knowing that using continuity equation and expressing our velocity 1 and velocity 2 in terms of your flow rates, and doing some algebra, we finally get an expression Q is equal to K to 2G over 1 over A2 squared over A1 squared P1 over gamma minus P2 over gamma raised to the power 0.5. So again, Q is proportional to K, and the value of the K depends upon the type of orifice meter that you have. So you're going to make use of some of your experiments to calculate K. And then once you get the K, you're gonna check the validity of that K and see how well this orifice plate measures the flow rate. in your pipe system. The rotameter will be the third device that we'll be using, and the rotameter essentially is an inline flow measurement device, and it's got a little float, and it's got a graduated scale. And what happens is, as water flows through the pipe, water is flowing from bottom to top, and as it moves, it pushes this plate. It pushes this float up due to the drag forces of the fluid, and then the gravity tends to push that fluid down. And if you also notice, the cross-sectional area up here is much larger than the cross-sectional area here, so there is a differential velocity which causes that drag force, and there is, at some point, the drag force is balanced out by gravity, and the rotameter settles. So once we measure where that rotameter has settled, we again, can use a calibration. We can, by using known flow rates, we figure out where this rotameter is actually settling, and then we create a calibration curve and use that calibration curve to estimate other flow rates. If you were to buy a rotameter commercially, the manufacturer would provide you with a calibration curve that would tell you where this rotameter would settle for a given flow rate, and you use that to measure flow rate. So you're not directly reading flow rate, you're reading the length at which that rotameter has settled, and that length is proportional to the flow rate. So again, it balances out the drag forces and the gravity forces for that float to settle. The other flow sensor that we'll be using is what's called as a Hall effect flow meter or a flow sensor. And what Hall effect essentially says is that if you pass current through a magnetic field, the magnetic field pulls the electrons in one direction, so this causes a voltage pulse or a voltage drop. So the way the Hall effect flow meter is constructed is we have a turbine with several blades, and one of the blades actually has a magnet on it. So this blade has a magnetized rotor, and the casing assembly has another magnet associated with it. So when that rotor that has the magnet comes into contact with that magnetic assembly, it creates a voltage pulse, and then we use a microprocessor to measure or count that voltage pulse. Okay, and clearly the more flow that's coming in, the more quickly will this turbine rotate, so there will be more voltage pulses which we count, and then we take this rotation speed of this turbine and then link it to a flow rate. So again, we calibrate it to a known flow rate and then use that to make other flow rate measurements. So the idea is you create a voltage pulse and then count the number of times you're creating that voltage pulse, and that is a measure of the flow rate that we'll be using. So we'll be using this Hall effect flow meter to calculate flow rates as well. And of course, for all of this, the most fundamental way to calculate flow is to use gravimetric flow measurements. So we'll also be measuring it by collecting a known volume over a given period of time and use that to calculate our flows. So in this class, we'll be using a variety of inline devices and sensors to measure our flow rates. We'll be measuring it using a Venturimeter, wide-angle diffuser, Orifice plate, Rotameter, a Hall effect sensor, as well as the gravimetric or the volumetric method. We have used manometers to calculate the pressure differential before and after each of these apparatus. So that gives us an idea of what the pressure differential is, and then we apply Bernoulli's and continuity equation to get our unknown flow rates. So pretty straightforward. We'll be taking a lot of manometer measurements. We'll be taking measurements to get our volumetric flow measures, as well as reading of the rotameters. and using a data acquisition system to calculate, to measure flow rates using our Flowrate sensor, or the Hall effect Flowrate sensor. So that is the gist of the experiment we'll be performing in this week's lab. Thank you.